Hello and welcome. In order to use the method of partial fractions, we need to be able to break the denominator down, so factor the denominator. But what happens if the factors you get are not just linear factors like we were just looking at a moment ago in examples 1 and 2? So for example, what if you have a repeated linear factor, one that's raised to an exponent, or an irreducible quadratic factor, or a repeated irreducible quadratic factor? Well, that's what we're going to look at here. So if you have a repeated linear factor, something of the form x minus r to the m, then you're going to have as many little fractions as your power of m. So if m is a third power, you're going to have 3 of these little fractions. We'll look at that in a moment in example 3. If you have an irreducible quadratic factor, so something that you just can't factor any further, so it's an x squared that can't be factored further, then the corresponding fraction, the fraction that will correspond with that, is going to be something of the form ax plus b over your irreducible quadratic factor. Again, we'll look at an example there too. And if you have a repeated irreducible quadratic factor, one where the quadratic factor is raised to a power, like 2, 3, 4, then you're going to have as many fractions as that power, just like in the repeated linear factor case. But in this case, we have an irreducible quadratic factor underneath each of them, and above each of them, you're going to have something of the form ax plus b. Here, they're subscripted 1, 2, 3. That's just so that we can write an unknown number of them. But most of the time, we'll write ax plus b, cx plus d, ex plus f, and so on. So let's jump into example 3. Here what we're looking at is a linear factor. So x plus 2 is a linear factor. So it's something in the form ax plus b. But it's repeated, in other words, raised to an exponent twice. So raised to an exponent of 2. So what we're going to do is first focus in on breaking that fraction out into the sum of littler fractions. So we've got 6x plus 7 over x plus 2 squared. And the way that this is going to expand is like this. You see that exponent of 2, which means you're going to have 2 fractions coming from that. And above each of those fractions will just be a letter, a and b. That's because we're dealing with a linear factor here that's being repeated. So with linear factors, you just have a single letter above each fraction. And then down below, we're going to have x plus 2 and then x plus 2 squared. So you're going to have all the powers of the linear factor from 1 all the way up to the highest power. So if we had x plus 2 to the third, for example, it would be a over x plus 2 plus b over x plus 2 squared plus c over x plus 2 to the third. So the powers just go from 1 to whatever your exponent is. All right, now the same kind of technique applies. First, we're going to clear the fractions by multiplying both sides by, in this case, x plus 2 squared. That clears out the little fractions and the big fraction on the left as well. And so we're left with 6x plus 7 equals a times x plus 2. One of the x plus 2's cancels, and you get one of them left. And then plus b with nothing left over. Now from here we have the two options. We can either distribute everything out, combine like terms, and match the coefficients of like terms, or we can plug in specific x values to help us isolate certain undetermined coefficients. Let's go ahead and see what that the second method looks like here. Like what would be an x value that you could plug in order to get rid of one of the undetermined coefficients? If you said x equals negative 2, that would be correct. Because when x equals negative 2, x plus 2 becomes 0, times a is 0. And so all we would have left is b. Let's see what that looks like here. Plugging in negative 2 on the left side, we'll have 6 times negative 2 plus 7. On the right side, we'll get 0 plus b. So from this, we get b equals negative 5. Now, when we were doing it in example 1, there were other x values that we could plug in to get the other undetermined coefficients. But in this case, there's not really anything attached to b, so there's no way we can get rid of b. But that doesn't stop us from plugging in any other x value. Like, I'm going to go ahead and just plug in x equals 0. That's pretty easy to plug in on the left side because we just get 7, right? 6 times 0 is 0, plus 7 is 7. And then on the right side, we've got, well, a times 0 plus 2, so that's going to be 2. And then the b value, we already know. We just figured out b is equal to -5. So solving this for a, we get a equals 6. There we go. All right. So now that we've got the undetermined coefficients, we know exactly how that original fraction breaks down into the two smaller fractions. So now we can write the integral, the original integral, is equal to the integral of plugging in a equals 6 back into a over x plus 2. We have 6 over x plus 2. Then plugging in b, which is -5, into b over x plus 2 squared, we've got minus 5 over x plus 2 squared, quantity dx. So now we can go ahead and integrate term by term. This will be easier to integrate term by term. On the one hand, we just have, I'm going to make a little bit of room to handle the second integral. On the one hand, we have 6 times the integral of 1 over x plus 2, which is ln, absolute value, of x plus 2. Now for the second part, a common mistake would be to think whenever you integrate 1 over anything, it's just ln of that thing. That's not really the case. Because remember, if you want to check your work, you can always take the derivative and make sure that you get back to the original function. And in the case of ln of x plus 2, that works. You know, the derivative of ln of x plus 2 is 1 over x plus 2 times the derivative of the inside, which would just be 1. And so it works for that. But it wouldn't work if you just wrote ln of x plus 2 squared for that second function, second fraction. If you try taking the derivative, you'll find you don't get back to this function. So instead, what we're going to have to do to evaluate the second antiderivative, or integral, is a substitution. We're going to do a little u substitution to help us out here. So let's write that right underneath it. So we're focusing on the integral of 5 over x plus 2 squared. And I'm actually just going to write down 5 times x plus 2 to the -2. Because then when we let u equal x plus 2, the du is just dx. And the integral turns into 5u to the -2 du. So then when we integrate, we can just add 1 to the exponent and divide by that new exponent. And you end up getting a -1 for the new exponent. So when you divide by -1, you get -5. So 5 divided by -1 is -5. U to the -1, I'll put a little plus c here, but this is just some side scratch work. And so then we end up getting -5 over x plus 2 plus c. So here we have -5 over x plus 2, and then we'll put our plus c at the end, and we're done. With a slightly crooked answer. Okay, so thank you for watching this part, and we'll see you in the next part.